Hello, and welcome back to Calero Academy. Today, we are going to be looking at a very fun and practical problem, which deals with fuel economy. Note that this problem was based on a problem taken from the textbook Stewart's Calculus. Okay, so the problem is practical because, again, it's based on the matter of fuel economy, which is very important to most people because we spend a huge amount of money at the pump. The problem gives us two functions, c and g. Well, it doesn't give us g. So anyway, the function c is going to be called the consumption function. Now, the consumption function just says how many gallons are you using per hour, per some time interval. So we write c is going to be equal to some gallons used over a certain time interval t sub v. Note that, of course, c is going to change if you are going at different speeds, and therefore c is a function of v, where v is equal to miles traveled at some speed v, over some time traveled at speed v. So g, the function that we are going to be looking at a lot, is going to be our fuel consumption function. So it just says how many gallons are you using per mile. So how many gallons are you using per mile? So we can write that as g divided by m. Now, the problem asks us, find what value of velocity minimizes our g. Or, in other words, how fast should we drive some distance to minimize our fuel costs? So, the way we are going to do that is by expressing g in terms of c and v. So, because the problem tells us that we know what c is, and we want to find g, of course, the minimum of g. So g is equal to g on m, as we said, which is also equal to g on t sub v divided by m on t sub v, which is equal to c on v. So we can rewrite that the function g of v is equal to the function c of v on v. Now that we have our function g expressed in things that we know, we can now try to minimize g of v with just some differential calculus. So we can write that dg dv, the derivative of g, is equal to the derivative of c, the derivative of c times v minus c over v squared, where we just employed the quotient rule. So remember that to find the minimum, to find the extrema of some function, we have to take the first derivative and then set it equal to 0. So let's set this equal to 0, and after a little bit of algebra, we will get that g of v is an extrema when dc dv is equal to c on v, where v is going to be equal to our special velocity, v star. So it's saying that at this special velocity, dc dv is equal to c on v. Now, to determine whether this is going to be a minimum or maximum, we now need to take the second derivative at v is equal to v star. So our second derivative is dg the second derivative of g with respect to v. So this is equal to the derivative of c times v minus c with respect to v times v squared minus 2v times the derivative of c times v minus c, all divided by v to the power of 4, where we just employ the quotient rule again. So now, we need this to be more than 0. For this to be for v star to give us a minimum g, we need this to be more than 0. So, note that v to the power of 4 is obviously going to be a positive number, because there's no way we are going to see complex numbers for our velocities. So this does not affect the sign of this entire expression here. It's going to be positive or negative regardless of what this is. So we can reduce this, so we can take this out of the picture. Next, let's note that this, inside the derivative of c times v minus c, is equal to the numerator of the first derivative. Now, since we're taking the second derivative at this special value of v, we should put it like this, v star. Since we're doing that, we can substitute in what the first derivative is at v star. The first derivative at v star is equal to 0, and therefore this is also equal to 0. And therefore we can simplify this entire expression as the derivative of c times v minus c with respect to v times v squared, and all this stuff turns to 0 at our v star. So we need this to be more than 0. Note again that v squared is also going to be positive, so we can take that out of our expression too. Now, all we need to do now is take the derivative of this, which is going to be equal to the second derivative times v minus c, plus the derivative of c minus the derivative of c. And we need that to be more than 0. Now these obviously cancel out, and now, again, look, v is going to be bounded below by 0, and we can safely assume that v is going to be positive, since this is a practical problem, and we are never going to see a velocity with negative speed. We're never going to see a negative velocity, and we're unlikely to see a velocity of 0. So this also does not affect the sign of this expression, and therefore we can write that at v star, the second derivative of c has to be more than 0 for our g to be a minimum. So we can rewrite that if the first derivative, if dc dv is equal to c on v, and at v is equal to v star, the second derivative of c is more than 0, then we have our minimum of g, our minimum g. So, and this is going to be our beautiful answer. Now, let's note two things. First, in the real world, if the function c roughly resembles this in the real world for most cars, where this is 20, 40, 60 miles per hour. So the minimum of c usually occurs over here, and therefore g star will look to be somewhere around here, because c on v will roughly match the actual derivative of the function there. And that actually turns out to be quite true. The real world minimum for G, or in other words, the speed at which our fuel costs are minimized, is roughly between 60 to 80 miles per hour, which is roughly around the speed at freeways. So that is the first nice practical note, that this has a really nice real-world application. The second note is that if c was to resemble, say, was close to the function e to the power of x, then we also have a very nice and beautiful way of expressing this, that our second derivative had to be equal to, that our second derivative would be equal to our first derivative, which would be equal to c on v. So that's just another nice thing to look at. And that ends this Calero video. We hope you enjoyed it. If you spotted any errors, or if you had any questions to ask, please just put it down in the comment section and we'll hope to get to you on that. So, thank you again,